This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Material science is transitioning from trial and error discovery toward autonomous systems that stabilize plasma fields into precise geometric boundaries. This shifts production from an empirical process to a mathematically grounded infrastructure, where synthesis is no longer dependent on human observation. The Ω-Reactor serves as an autonomous, cybernetic execution engine designed for high-precision material synthesis. This diagram shows the sub-10 millisecond firmware loop, which resolves the governing partial differential equations of the plasma state in real time. Using hybrid Model Predictive Control, the system monitors input vectors like microwave power and gas ratios to optimize the physical state against those equations. At these speeds, real-time physics control eliminates the latency and error inherent in manual empirical synthesis. The system identifies and annihilates structural flaws during formation, preventing defects from propagating. This NAP integrates Raman and Optical Emission Spectroscopy data to visualize structural integrity. Sensor streams plot atomic deviations in real time. Applying defect manifold theory, the system isolates stacking faults and sp2 carbon inclusions, physically suppressing them until the surface reaches a uniform plane. This process transforms material purity from a statistical likelihood into a calculated certainty. The operational stability of this autonomous network is grounded in formalized mathematical proofs. This is the bridge runtime closure theorem, a formal proof that the system's computational and physical loops remain closed and stable. It mathematically guarantees that physical defects continue to contract throughout the production cycle without the need for any human intervention. This formal proof of closure allows for industrial scaling across nodes without the degradation of material quality. This architecture scales from a single core to synchronized multi-node synthesis clusters. Every physical asset receives an immutable cryptographic hash. It encodes the material's defect history and specific control parameters into this trace chain. This exact cryptographic record, known as scroll DNA, formally converts the raw physical material into a perfectly verifiable tokenized ledger. Linking material precision to a cryptographic trace secures the supply chain against counterfeiting and structural degradation. Deploying this autonomous material stack is required to maintain parity with current materials' capabilities. Achieving precise computational control over the physical substrate provides the ultimate foundation for advanced technological and economic infrastructure.